Hey everyone, welcome back to math. The first three lessons have focused on solving quadratics. The first lesson we talked about solving quadratics by factoring. Then in the second lesson, we talked about solving quadratics by a direct method of the square root method. And then in the third lesson, I introduced the idea of the quadratic formula. And remember, the quadratic formula always will work. It just tends to be very tedious and very long. A lot of things to plug in and a lot of places where we can make mistakes. So I think it's important that we spend some time doing some extra practice on that. And that's partially what this video is for. But we're also going to talk about a little bit more of the meaning behind a complex solution to a quadratic. What does that mean? Okay. So for our objective today, we want to be able to determine if solutions are real or imaginary. And that's kind of the idea. We're going to use the quadratic formula as our foundation to discover that. Okay, so first of all, remember that finding the zeros means finding the x-intercepts. Finding zeros means finding the x-intercepts. And if you remember, how do we find x-intercepts? Well, x-intercepts graphically are where a parabola or a function crosses through the x-axis. And we know that the x-intercepts occur when y equals 0. So here's an example that I want to go through here. Determine the zeros of the following function. So we have y equals x squared minus 5x plus 7. Now we want to find the zeros of this. In other words, we want to find the x-intercepts. So what do we do first? Well, if I want to find the x-intercepts, we set y equal to 0 and we solve. Okay. Now remember, I broke down the different ways or different methods that you could use. Remember, if you see ax squared plus bx plus c, you can use factoring or the quadratic formula. If you see ax squared plus bx, then you're going to use factoring with the GCF. And if you see ax squared plus c, where the b piece is missing, then you can solve this directly with square roots. In this case, we have an ax squared, a bx, and a c. So we can either use factoring or the quadratic formula. But I'm going to show you why factoring doesn't work in this case. Remember, we look for GCFs first. We don't have any GCFs, or at least the GCF is 1. So we go to the next step of doing the quadratic factoring. So we set up our x. A times c is 7, and then b is negative 5. So if we're to list the factors of 7, we end up with only 1 times 7. That's the only combination that works here. And so we can see that if 1 times 7 is the only one that works, well, 1 and 7 don't make up 5 or negative 5 in any way. So we would say that this is not factorable, okay? So that leaves us with the only option of using the quadratic formula. Remember, the quadratic formula says x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, okay? So if we can plug things into that formula, we'll be doing okay. So it's not factorable. We can cross all this stuff out, and we can focus on the values that I would plug in here. So a is equal to 1, right? The a value is 1. B is negative 5, and c is 7. So we're going to plug that into the quadratic formula. So this will say x equals negative parentheses, negative 5, plus or minus the square roots of b squared, so that's going to be negative 5 squared, minus 4 times a, so 4 times 1, and then times c, so times 7, all over 2 times 1. Now, in the last video, I showed you how to quickly shortcut through this and make sure you do these same steps every time to simplify. So we can do the negative 5, which is positive 5, plus or minus the square root of, well, negative 5 squared, we can do that. It's 25. And then 4 times 1 times 7, that's 28. And then we have the minus out front. Negative 4 times positive 1 times positive 7 is negative 28. And then all over 2. Okay, so we have that. And now we want to simplify this. So we simplify what's inside the radical. 25 minus 28 is negative 3, and then over 2. Now, this particular problem this particular solution cannot be broken down or simplified any further than what we have. Well, actually, we can do one more thing. I apologize. You have the negative inside the radical, so you can take that out because it's an imaginary number. We could say 5 plus or minus I radical 3 all over 2. So that is our answer. We could rewrite it as x equals 5 plus I radical 3 over 2 and 5 minus I radical 3 over 2. So those are our solutions, and I guess I shouldn't even box that in. But remember over here it says that we are looking for the zeros. We're looking for the x-intercepts. Normally, we write our x-intercepts as coordinates, remember? The problem is that our solutions are imaginary. We have two imaginary solutions or two complex solutions. Well, what does that look like on the graph? What does that mean? Let's go ahead and take a look at the graph of this parabola. So remember, how do we graph this parabola? We do negative b over 2a, find the axis of symmetry, plug it in, and then determine the vertex, and then we would graph this parabola. What I'm going to do, if I can do it, what I'm going to do is I'm going to go to desmos.com just so we can get a quick look at what this parabola looks like. So as I'm in Desmos here, I'm going to go ahead and type in my equation, y equals x squared, and then minus 5x plus 7. Let me shrink my screen down here a little bit. And we can see that this parabola, what are the x-intercepts? Well, this parabola doesn't have any x-intercepts. They don't exist. So that's what it means to have imaginary x-intercepts or imaginary solutions to a quadratic. It means that there are no real x-intercepts. Now, we can go a lot deeper with this, and there's actually something called the imaginary plane, where we do have two x-intercepts, if you would, that exist on the imaginary plane. We're not going to go into that at all in our Math 2 class. But what I need you to recognize is that if our solutions are imaginary in any way, then what we actually get are no real x-intercepts. We can see that there's no x-intercepts here, okay? So with that said, let's go ahead and go back to our lesson. So let me just double check my answers here. We've got x equals 5 plus or minus I rad 3 over 2. And you're going to want to write them separately because there are two separate distinct answers. And let me go ahead and add this. There are two imaginary, or we would also say complex solutions. Okay? There are no real x-intercepts. Okay? So that's that for this particular function. Okay? So here is, let's see, here is some practice problems that I would like you to do. Go ahead and find the zeros. Go ahead and find the zeros. And then when you think you have your answer, come back and watch the video and see how you did. All right, for number 1, we have y equals 3x squared minus 4x plus 8. And we are looking for the zeros, or we're looking for the x-intercepts. So we set y equal to 0, 3x squared minus 4x plus 8. Because we're doing practice with the quadratic formula, it makes sense that we should continue with the quadratic formula. But in reality, this one wouldn't be factorable either, okay? So, quadratic formula, we would say x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And then we'll plug our values in. So x equals negative, parentheses, b is negative 4, plus or minus the square root of negative 4 squared minus 4 times 3 times 8 all over 2 times 3. Okay, so we can go ahead and simplify that. We'd end up with positive 4 plus or minus the square root of 16, negative 4 squared is 16, and then negative times a positive is a negative. 4 times 3 is 12, times 8 is 96, all over 2 times 3 is 6. Okay. Then we'll simplify this further, so we end up with 4 plus or minus the square root of negative 80 over 6. Now here we have something that we can simplify further, not just with the I, but we can simplify that radical. And so we would break that down. The negative 80, one of the factors is obviously negative 1. And we have 2 times 2 times 2 times 2 times 5. If you need help factoring that to the primes, I would recommend watching a video from Unit 4, simplifying radicals, okay? And then we're going to go ahead and circle our pairs. So we got 4 plus or minus, and then we'll circle our pairs. We've got a pair of 2's and another pair of 2's. So one of each of those goes out. We'd get a 4 on the outside, and then the negative 1 turns into I on the outside, and then radical 5 all over 6. One step to go. We need to see if we can reduce this in any way. Is there any common factors out of the whole thing? Well, the top are all even numbers, 4 and 4, and the 6 is even. So we could actually divide the top by 2 and also divide the bottom by 2. We can simplify those. And so we end up with x equals 2 plus or minus 2i radical 5 all over 3. And so we would separate those answers to say x equals 2 plus 2i radical 5 over 3 and 2 minus 2i radical 5 over 3. And so we can see again that we have two complex solutions. And because we have two complex solutions, we have 0 real x-intercepts. If you were to graph this, you would see there's no x-intercepts in number 1, okay? All right, for number 2, we have y equals x squared minus 6x plus 7. Looking for the x-intercept, so 0 equals x squared minus 6x plus 7. Just a side thing, I just thought about this to think about. You can't use the quadratic formula unless the equation is equal to 0. So if for some reason you have something that's not equal to 0, you're going to have to move that over so that it is equal to 0. You're going to have to solve for 0, okay? So x equals negative b, so it'd be negative 6, plus or minus the square root of b squared, so negative 6 squared, minus 4 times a, times 1, times c, which is 7, and then all over 2 times a, so 2 times 1, and then we can simplify this to be 6 plus or minus the square root of 36 minus 28 all over 2. So x equals 6 plus or minus the square root of 8 all over 2. Now, something I want you to recognize, and I think you might have already seen this, but you should see that our axis of symmetry, remember our axis of symmetry, the equation for that is x equals negative b over 2a. Well, that's the very first part of our quadratic formula. Let's go over here. With our quadratic formula, we can see our axis of symmetry is hidden inside this formula here, negative b over 2a, okay? So that's kind of cool. In other words, 6 over 2 is our axis of symmetry of this particular problem. But that's a side note. I'll get more into that in just a minute. So we end up with 6 plus or minus radical 2 times 2 times 2 all over 2. And so we have x equals 6 plus or minus 2 radical 2 over 2. And then we can simplify this a little bit because all of these can be reduced by 2. So we'll divide all of that by 2. And we end up with x equals 3 plus or minus, you could say 1 radical 2, all over 1. But that all simplifies to just say x equals 3 plus or minus radical 2, okay? Or we would write it x equals 3 plus radical 2 and 3 minus radical 2, okay? So now check this out. This has two real solutions, which means we should have two real x-intercepts. There is no imaginary numbers here, so these solutions are real, which means we should see on a graph an actual parabola crossing through the x-axis. So let's go ahead and verify that. Remember, the axis of symmetry was negative b over 2a, and I'll go ahead and do it, but it was going to be, let's see, negative b, that'd be negative 6 all over 2 times 1. So that's 6 over 2, which is 3, okay, which is 3. And that's exactly what we see with the first part here, the b, negative b over 2a here. We get 3. But then we plug that in to our equation. We get y equals 3 squared minus 6 times 3 plus 7. And then exponent, so that'd be 9 minus 6 times 3 plus 7. And then 9 minus 18 plus 7. So that'd be negative 9 plus 7 is negative 2. So we know that our vertex is going to be 3 comma negative 2. When we go to graph that parabola then, we're going to go to the right 3 and down 2. And from there, we're going to follow our slope pattern. Since the a value here was, way back up here, the a value is 1, the slope pattern is the regular 1, 4, 9. So we're going to go up 1 over 1, up 1, 2, 3, 4 over 2, and up 1, 2, 3, 4, 5, 6, 7, 8, 9 over 3. We'll reflect onto the other side, and we'll graph our parabola. Okay. Well, what do we see here? We see that we have two actual, real-life x-intercepts. We have one somewhere right here and somewhere right here. Okay. Now, if that's the case, we should be able to calculate those. Notice our solutions here were 3 plus radical 2 and 3 minus radical 2. So I'm going to go ahead and use my calculator, and I'm going to figure out what those two values are in decimal form. Because they're on the graph, I might as well know what they are. So we're going to say, first of all, I'm going to do radical 2. So second radical 2, and hit enter. That's 1.414. So my answers then would be 3 plus 1.414 and 3 minus 1.414. Okay, so that turns into 4 plus 4.414, and I'll do this one, 3 minus 1.414. We end up with 1.586. So our actual x-intercepts here are going to be 1.586 comma 0 and 4.414 comma 0. Okay, so if we go back to our graph, we should be able to see 1.586. If I go over 1 and about a half, I see my x-intercept. If I go over 4 and about a half, I see my other x-intercept. So here we have two real x-intercepts, two real solutions. All right, that wraps up this video. I hope that give you good practice with the quadratic formula and recognizing imaginary solutions versus real solutions and what that means on the graph. Okay, if you have any questions, please comment below or find me in a tutoring session. Otherwise, I'll talk to you all later.